Okay, but we are ready to continue on your schedule, and now Felix will talk to us about solving in rings and what he did about it.
Thanks. So, yeah, a bit of context. So I'm a agda user since maybe 2013, something like this. And I'm a mathematician, and I'm not an agda implementer yet. So I hope to finally get into this. So that's one reason I'm here. And Andreas had the idea that I could talk about the solver I've written for the cubical agda library. And I thought that's a good idea because here there are certainly a lot of people among you who can tell me how to do it better, because I did something that's not exactly in my area of expertise. I mean, I know commutative rings very well, but the automated solving part, that's what I didn't know, and what I guess is still pretty ugly the way I did it. And what I'm also interested in is how can I do it better? Or are there modular ways to do something like this? And the meeting works very well. I already got answers to that. So I heard there's this framework called Frax of free extensions, and I looked a bit into it, and it looks like it might be the kind of thing I'm interested in. So if you view the talk now and you know later if I should check it out or not, then please let me know your opinion. And one thing I also want to improve is how I deal with reflection. There I basically did the monkey see, monkey do strategy. So I just copy-pasted what I found in the standard library and hacked around until it worked. And so that's pretty ugly, and I probably should improve it to make it more usable for other people. So my intention here was not, at least originally, was not to write a solver for everyone, but only to have a tool for myself. And the more I thought about it, what I should tell you exactly, I thought it might be actually kind of more interesting to some people why I need a ring solver in cubical agda. So I think it's good to spend some time about it, but contrary to the title, I actually start with the what. Maybe what do I want to do? So here it's written down in mathematics, you have a commutative ring and maybe some abstract elements, some variables. And now you don't want to prove something like this yourself by hand, where yourself by hand means something like this. So that's actually the wrong example. Let me go down a bit. So this is actually a file on non-necessarily commutative rings in the cubical library, and I picked it because there is no stuff like this for commutative rings now because there's a solver and it's not needed anymore. So I had to look here for proof that is, I mean, it just uses plus, so it's a bit boring, but it's really something that just uses ring axioms and zim and kong and yeah, shuffles two pairs, like the name says, a bit around in a way you need somewhere. I think it's used when you construct a quotient ring, maybe somewhere else as well. So just some small calculation. And I mean, in the beginning, when I started to work on my algebra project in cubical agda, I was pretty happy to do stuff like this. It's kind of nice memories, how you did this on paper as a math student, so it's okay. And I just thought to myself, okay, I know there exists stuff like solvers, let's just wait until it gets annoying. And it got very annoying when I tried to construct localizations of rings. So there I thought, okay, that's really too much. And I started to write the solver. But first let me show what the solver is supposed to do in a situation like this. So I artificially put exactly this example in here. So the solver, well, it should save you from having to do this proof, and yeah, this type checks as is. And it can do more complicated and bigger stuff that works. I think if you add like double of that, it takes too long, but no wonder, because it's written very inefficiently, as you will see. But in practice, I never needed something that's actually even that long. So I didn't care to improve it so far in speed. Okay, so that's what it should do. And there's a lot of work to build on or to just copy from, I thought. So here's an old issue which says ring solver, which is a bit imprecise because it's really about a solver for commutative rings, and having one for non-commutative rings is, I think, a lot more work, so, but also doable. And he wrote, I'm not sure how to pronounce his name, Donaka or is in Kidney, maybe. He wrote a bachelor thesis and implemented one solver for commutative rings, which got later merged. I'm not exactly sure what the status is into the standard library, but I think it's merged. And he put a lot of effort into making it nice to use, and yeah. And I looked at his code to kind of extract what I need and just have something which works. So, but he has written a very nice bachelor thesis on this very good code. And he said he based his work on proving equalities in a commutative ring done right in Coq. So that's an older paper which I also looked into, and which has some nice ideas. So they define a structure called almost ring, which for them also covers the natural numbers, which are not a commutative ring because they don't have additive inverses, but they have a nice trick of still doing everything once for these rings and similar rings and so on. So that's nice, and in principle, I followed their approach. Yeah, but there is a problem. Let me go back to this example file where I have my tests for the solver. As you can see here, the ring I'm proving stuff about is just a variable, basically. So it's not like a ring I actually concretely have, like the integers. It's just a variable. And it turns out, if you look at those papers and those ideas I just mentioned, and you just implement it, like the easiest path you can see, you get something which actually doesn't work in this case. So that's a problem I want to go into later. But now, as an intermission, I want to talk about why I wanted or needed a commutative ring solver in the first place. So usually your hot homotopy type theory is advertised as something that gives you an internal language for infinity group voids, or a synthetic language for homotopy theory. So you can talk about in an abstract way about things people studied in topology, and that's all very nice. So also something I enjoy. But there's other maths I might even enjoy more. And there's also a way to use hot for that. And to do this, you need to know that hot interprets not only in this higher category, but also in much more complicated ones, or much more interesting ones, bigger ones, whatever you want to call it. And here's one which contains objects which are of interest in algebraic geometry. So if algebraic geometry doesn't tell you anything at all. It's a very big and important branch of pure mathematics, and it's important in geometry, in algebra, and in number theory. And I don't want to do much, don't worry. So just writing down equation. So you believe me, I'm a mathematician. So this is the equation from Fermat's theorem, and he conjectured and claimed to have proven that for n bigger equal to 3, there are no non-trivial solutions in the integers for this equation. And it was proven as a consequence of some more abstract theory, and this is like a phenomenal ton amount of work which went into this more general theorem called the modularity theorem, and most of it is algebraic geometry. So yeah, it's important. It can help you to solve problems just in numbers by using methods from geometry and from homotopy theory, actually. So that's interesting twist in the history of mathematics, that you can combine stuff like this and it makes a lot of sense. Yeah, okay. And my approach to kind of simplifying algebraic geometry, I mean, it's infamously hard. You have to learn a lot of different things because, well, you work with sheaves on complicated spaces, and then you need one-types, what we in Hot would call one-types, and that's very hard to do if you are on set level in some category of sheaves. Then you need to define higher sheaves, which people did in the 60s for level 1, and they saw it's still very useful, even if it's horribly complicated. You have to do everything with a big sack of coherences you have to carry around, and if you want to be formally precise, you draw diagrams which are page-filling all the time to do the simplest stuff. And that's a bit satisfactory because it works, but unsatisfactory because it's formally so complicated. And what people usually do is they just simplify stuff in a way that doesn't even type check when you try to read it in an article or even in the introductory literature already. You have a lot of stuff that it just isn't right, but is morally right because you can expand it with enough coherences and then make sense. So that's a bit sad. And if you use Hot, you can do it. You can use just the identity types to do things like this. But then it becomes hard again to talk about algebraic things. But that's something I'm currently doing with Thierry Cocor and Matthias Hutzler in Gothenburg, and it seems we have found an approach which works well. And yeah, it's based on work by Ingo Blechschmidt, whose work is based on like a side branch that existed, a very small one in algebraic geometry, like almost from the beginnings. And yeah, there was work by Hakim and also Koch from the Koch-Levy axioms, if you heard of those, for synthetic differential geometry. He also tried a bit synthetic algebraic geometry. Yeah, so that seems actually to work. And the nice thing is, compared to synthetic differential geometry, which is also nice, but kind of got rejected by mainstream mathematics because you can't use it to prove new stuff. You can only use it to make already known stuff easier because you have so much catching up to do that you can't do it as a small community. But here you actually have a chance to jump to the current level of research. Why? Because you can use synthetic homotopy theory and synthetic algebraic geometry both together. And that's very useful because you kind of eliminated two things which are very hard to do formally, and now you can do it formally. And then, yeah, this works. And last comment on that. Why hot? I mean, higher types appear actually in two different ways. So one thing is, you might have heard, are modular spaces in algebraic geometry. They really are from the morality of the story, they are just collections of things. But they turn out to be one types because they are collections of zero types. And that was incredibly hard to do back then formally. But here you can just take a sigma and just collect stuff and it's all fine. And you get a one type, but who cares, you can deal with it in hot. And the other thing is cohomology, which might even be more important. So you might have heard over here, so in this line, that you can define cohomology in hot very easily by using Eilenberg-MacLane spaces, which is given just by doing some simple high inductive types. And you can do the same thing here, that also works here, to repeat in some not so straightforward ways, but it turns out it works very nicely, so you can do the same constructions here. You just put in more complicated stuff, but it still all works out. And you can deal with cohomology in here and shortcut a very big pot of things you usually do in algebraic geometry to define cohomology even and then to work with it. To do a lot of work. Yeah.
And when you say one type, which indexing of n types are you using?
It's one above set.
So
I thought that's more common, but I mean, yeah, you might be cubical acda user and yeah.
Yeah, I am a cubical acda user.
Yeah, then it's three. Then it's three.
Mathematicians aren't that positive about propositions.
No?
Mathematicians aren't that positive about propositions.
Yeah, right. It's just a bit weird that it starts at -2. But
Yeah, okay, good. Yes, so that's why, and now, okay, yeah. I mean, if I'm working here, what turns out to happen is that I have to do a lot of algebra constructively, and I want to do it in cubical type theory for the homotopy theory. And so I'm naturally in the situation where I do constructive algebra and have to use cubical acda, or can use cubical acda, so it's very natural choice in this case. Yeah, fortunate coincidence. And just a list of examples, what things come up when doing this internal algebraic geometry. I mean, these are the easy things, quotient rings, polynomials, and I did a lot with finitely presented algebras, which just means you have a polynomial ring quotiented by finitely generated ideals. And I needed to show some closure properties and some examples to get something done. And then localization of rings. This was a neat surprise. So when I told you earlier, when I saw localizations, oh my God, I have to prove this big equations all the time. I don't want to. I started to do the ring solver, but then in parallel, someone else, Max Zeuner in Stockholm, he started to actually just implement localizations. But later on, he already started to use my half-finished ring solver to get some shortcuts. And now it actually turns out I didn't use this ring solver so much myself, but people used it to do stuff I wanted the ring solver for, so it's all good, and yeah, very neat that things happen like this. Okay, yeah, and sometimes, which is constructively not so easy as you might think, if you remember rings like this from algebra, so you have some Laurent series here, but alone to see that a polynomial is really some kind of sequence of coefficients or something like this is constructively already quite some work, depending on where you started, of course, your definition of polynomials, yeah, but yeah, things like this actually take some time, and then you are really happy to have a ring solver to at least shortcut
How to
this more
decipher
calculation.
this is a ring of polynomials in one variable?
Yeah, that's in one variable, and then you invert at one element. So you quotient, you are allowed to quotient by x. Maybe I wrote it, I should have written it without the parentheses. That's actually not the standard.
You can also use comma x inverse, which is kind of
Yeah.
more like
Yeah,
inside
that's
the,
maybe
the square.
more. So, yeah. What I meant is, yeah, you have x and x inverse, which you can build as a quotient ring, and then it's actually annoying to show that you have kind of polynomials in x plus a polynomial in 1 over x or something like this. Yeah, so that's, yeah. So back to the ring solver, how does it work? It's the same approach as seems to be the case for all solvers I've looked at so far. You want to prove an equation, so you have two sides, and you start by translating your term in agda, which denotes some ring element, into some abstract syntax tree, like some inductive type for expressions, and then you compute a normal form, which in this case is the Honda normal form, which turns out to be pretty okay for this task. And you do the same thing to the other side, and then you just ask agda, are the normal forms equal? Because they still contain some coefficients. So agda might be able to unify those, and then you have an equality between the normal forms. And what you need to do to make the solver work, so the most work apart from using reflection is proving that this is sound, so to say. So you have to prove if you take some expression, compute its normal form, it will be equal as a ring element if you evaluate on both sides to what you had over here. So that's the approach. Maybe you have some example written below it. No, let's start with looking at concrete code. So here's the algebra expression, and so the upper one, mark it. Is this visible? No, it's also wrong. Yeah, okay, so yeah, here's already a refined version. So you could kind of start with just some ring and compute this Honda normal form and hope that agda will be able to unify the coefficients. This works if you have a concrete ring, then it can work very well. If you have, for example, inductively defined integers, or if you have a more general thing, inductively defined natural numbers, that works well. Then agda can unify the coefficients in the Honda normal form. But if you don't, if you just have an abstract ring, your coefficients might be ending up something like the 1 in the ring plus the 0 in the ring, and on the other side, just the 1. And then agda can't unify because it doesn't know anything about plus 1, 0, because it's all just variables, more or less. So what you need to do is to introduce some ring of coefficients where you can compute. And my first thought was, okay, I don't want a ring solver. I guess there, being a mathematician happened to me. I thought, you really have an algebra of a ring. And that's when I wrote this. But later on, it turned out I actually always want to use this only with the integers, and I didn't need anything more ever. So you can kind of think of the integers here, and then you just have something which constructs constants, And here I just use the base ring. So this A here, which is called an algebra, is the actual ring you want to solve in the end. And this R is just some coefficients, integers, in the usual case. And then this gives you constants, which are from the base ring. So in my solver, you only have integer constants, which turns out to be enough. I mean, it should be easy to generalize to arbitrary ring elements, but I haven't had the need for it ever so far. So I didn't do it. And this is the Brown index presented variable, and here you just have quoted ring operations, plus, times, minus. So we chose in the cubical library to have minus as an, I'm actually not sure, maybe I just chose it here. I mean, I think it's part of the ring structure.
But A is now a phantom type here.
A is a phantom type, okay. What does?
Because you don't use it in the data. It's just an extra index
Yes.
expression.
Okay. Does it mean it's bad to have it? Or?
Or you could simply drop it and you get the same type of expressions. Only now you have restricted it. I mean, I don't know what the phantom type is used for. Right?
Yeah, I mean,
in your evaluation function.
yeah, it uses it at least. So.
But yeah. Yeah, right. But it could be confusing maybe why this A is needed.
Yeah, it kind of makes sense mathematically that it's not used, because in the end it turned out I'm actually only looking at polynomials with integer coefficients in the end. So, yeah.
Is this due to the fact that the integers are kind of a universal mathematical object for the structures and like this?
Yes, I think that's kind of where it comes from. I mean, the universality already gives you, so maybe let's just write it down a bit. So if, let's say, S is a ring, so that S is a ring, so we always think commutative, then S is an integer algebra. So, I mean, that's the first thing that you want to have, because then you can plug it in above. So any ring is an integer algebra, so you can use this in the right way. And I mean, cases where you could make use of other coefficients are, for example, if you know 1 plus 1 is 0 in your ring, you could use bool with its ring structure as coefficients and might be able to use this, but I never calculated anything with that. But if you would do that a lot, I think it would be worth it to instantiate this for a different ring, different coefficient. Yeah.
So if I understand the idea, so you need a concrete ring in order for the solver, so you are doing it on the free ring. You create like a concrete ring, which is the free ring, and then you map it into use the universal property of this freely constructed ring to map it into the actual ring that you have. Is sort of what's going on here?
Yes, kind of. I mean, you could interpret what the solver is doing if you only use integers as calculating in polynomials with integer coefficients. So, I mean, to write it down, it's something like this. And if that helps anyone. And this is actually, in some sense, the free ring in n variables, because polynomial rings are free algebras, but you can reinterpret rings as algebras over the integers. So that's the free ring in n generators. So yes, that's kind of the idea. And yeah, the code to large parts still allows you to switch bases, but I never needed it. So all the proofs, all the hard stuff is only done for the case integers. Okay. Yeah, I guess this is pretty, how much time do we have left? When did we start?
None.
Half past. None. Okay, yeah.
And yeah, 5 more minutes.
Okay. I don't think I need it. I mean, maybe. Yeah. But yeah, maybe this is the best thing to talk about. Yeah. So there are a lot of things I would like to have, which build on top of that. Maybe a good short intro to what is actually the meat of the thing. So let me show you the normal forms, which are kind of short. So I guess you can even simplify it a bit more. So this 0 is something I introduced as something extra, so I don't have to rely on using const 0, which works well for integers because there I can decide if something is 0, but I was a bit scared to do it in general. But I'm not even sure if you can just drop the 0 polynomial, because if you drop it, I think you might have to introduce some weakening for the levels. So this level here, this n, is how many variables you have. And yeah, this is something you can read verbatim. So this is how the Honor normal form works. You decompose a polynomial, so you can read the degrees here. So if you have something of higher degree in the left and one lower on the right, and then you get something of higher degree. So it's basically a list of coefficients, but not done in the usual way where you just write a polynomial as a sum, but you kind of associate inwards and draw out coefficients. It's a bit rearranged. And this is good for multiplication, which turns out to be the most annoying thing. So, I mean, this dot h up there, that's multiplication of these Honor forms. And as you can see, I have to like mutually recurse with multiplications with constants. So that's a bit awkward. And then I have to make checks for if something is 0. Because if you multiply naively, you end up having like 0 polynomials written in complicated ways or ones in front of something. And that's what I struggled with in the beginning, to make the solver really solve all cases it should solve. Yeah. Yeah, what I should definitely mention is, I don't know how this is done in Coq. I think they also have coefficients, but I think the solver in the standard library is actually more better for the case where you have a concrete ring. This is better for the abstract case, but it's also something which exists since a couple of days or weeks in the OneLab. So that's also a place you should look if you want to understand solvers like this better, because they have a very nice explanation of their nut solver that's very well documented. So I think that's the best thing to read if you want to get into this kind of things. Okay, so yeah, scary multiplication with lots of checks that generates a lot of proof work, but now to the future. So there's something which I didn't really mention, but the solver can only like solve equality of polynomials, and if you have a given equation, something like x equals y plus 1, the solver can't use it. So you have to do it yourself. I mean, you have to use the solver to get back to the step where you use your equation, then apply it, then use the solver to go on. but you could actually write a solver that can use all polynomial equations and also use them reliably. But I think it's an insane amount of work that's not actually worth it. So what you have to do is you have to implement an algorithm which computes Gröbner bases over the integers, which I think is a lot of work to do in agda if you prove it, and things like this. So it's also a non-easy constructive algebra proof that this works. So that's pretty hard. But you might get around a bit by just calling some computer algebra system that can do it and just check that you have a Gröbner basis. I haven't thought too much about this, how much this would save you, but maybe that's a shortcut. And as I learned here, that's actually something you can do in principle from reflection in agda. So that's something that's probably too much work. Non-commutative rings would be awesome, but I haven't needed it so far, so should be doable, I think. And something which I'm wondering about, maybe someone has seen examples of this, it would also be nice to have a way to use homomorphisms. When I have a homomorphism of rings, I have a couple of equations. Can I make a solver that uses this kind of stuff without too much trouble? And yeah, that's not so important. I mean, in the future, I will probably need some slight extensions from rings to algebras or to R modules. Yeah. Okay. So thanks. That's it.
So first question, I didn't quite have time to get this. Iterated order forms had also parameter A. Was that also not used, or was it?
Yeah.
In that case, actually.
Yeah. I think that's also not used.
So that's also a yeah, red herring. I mean, there's no argument anywhere of that type in the data.
Yeah. I mean, yeah. Okay.
So it's just a syntax tree of
with coefficients in the integers. But I mean, if you look at what would actually be nice, would to have this, I think. So this would be kind of the general thing. Yeah.
Constants also from A.
Yeah. But
like generators.
Yeah. I left it out when I thought I will just get something working, and then to my surprise, I never needed it. So
because you already have the thin end, so you could sort of have a variable there and then later
yeah.
Because if you would insert values there, you would also probably want equations between them. I mean, or do you just treat them all abstractly? Yeah,
I mean, it could happen that I actually don't talk about a completely abstract ring, but have something where things compute. So, I mean, that would have been the kind of situation.
So then there are questions about a bit more this iterated order. So I didn't quite get, so this order of variables, how did this sort of, so is this, there's something with successor there, so it first takes care of, because there's like two things iterated at once. I mean, one is over the number of variables, and the other is about more the sort of degree of the polynomial in a certain variable.
Yeah, maybe. Yeah, it confuses me every time I look at it, so I don't know if that helps you also, but that's why this big comment is here. I always stare at this for some time. So, I mean, the idea behind is that Horner forms over some raw ring are raw ring again, so I can iterate and use them as coefficients, and that's how I get the the multivariate polynomials.
I guess an example would be about like 1 plus x times y. How that would look like, but that now we're out of time.
Yeah, so the iterated monoforms, they seem to be trees rather than lists, which is maybe confusing, right? If you look at the constructors for these, I mean the multiplication times x plus something, so those can again be full iterated monoforms, only that the thing after the plus has one variable less. But to the left you have all the variables still, so this is a bit confusing, right? So
Yes, this is confusing. I mean, okay, maybe I should write down a Honor form. I had one here in my slides.
yeah.
Maybe that's enough. So here you see a Honor form. I just wrote one because it turns out to be the same. And here you see you have a constant. So that's part of the Honor form, that this part is constant. And here you can have a polynomial again. And I mean here, in this case, in this instance of the constructor times x plus, you have a polynomial. But here it's a constant again. So the right is always a constant, but for the iterated Honor forms, it's a relative constant. So it means to have a n plus 1 variable ring, you consider n variable polynomials as constants, and that's what is n comes to.
That was what I was hinting at, that there was some sort of two recursions here. One is the degree in the polynomial in the n plus 1 variable, which is like the recursion on the left, and then the number of variables, which is a bit hard to go.
So this looks awfully similar to the Frex library we have in agda, which uses the algebraic notion of free extension of an algebra over a set of variables. So I'm wondering if it's possible to reformulate what you've done in this setting. Maybe it's easier to maintain at least.
I'm asking myself the same questions about the Frex library.
So
I don't know
Kamar is in this building, so maybe
yeah. So
it's a good
please
discussion.
talk to me about it if you think I should use the Frex library.
Any reason you're using dense cornered form instead of sparse cornered form?
No, just convenience. I mean, I just thought they might make it a bit more complicated, so I thought I don't use it until I run into speed problems. Yeah, but otherwise, yeah, sure, I should.
So I have another potential approach for generalizing this, which is something that I thought of a while ago, and I partially implemented, but then I sort of got sidetracked with other things, which is this might probably be right up your alley. Rings are, of course, just algebras over some Labir theory, and in general, I think you can do rewriting for Labir theories. You might run into problems with like how to deal with commutativity in this case, but as long as you don't have commutativity problems, and maybe there are some solutions for this that I haven't really thought about, you could actually then generalize this to all kinds of Labir theories, of course, if you have some automation mechanism for this. I have implemented large parts of that, but it's unfinished. So that might be interesting for you.
How do you know that you have like normal forms for your terms?
Yeah.
Right. I mean, this is the nice thing about corner forms is that they are sort of like normal forms of polynomials. And I'd be scared to like, if someone hands me a Labir theory and asks me to figure out whether things that have a normal form, I'd be like, well, maybe.
It's probably undecidable to know if your Labir theory has a model.
In general, this is, I think, the word problem, which is undecidable.
Like, try and do that for groups. Like.
But if you have some confluent reductions, then you're fine. And
Yeah, but the hard part is proving that your reductions are consequent, and that's where all of the creativity comes in.
yeah, in the commutative case, sure, then things are difficult. But of course, if you don't have commutativity, then for rings, for example, then it's kind of just trivial. You just shuffle everything to the left or something, right? So yes, in commutative cases, it's more difficult, and then you would have to actually work for it. But many other things you could get for free with this approach.
I guess what you're saying is in a way that you would refactor that so that part of it is reusable for other algebraic structures.
Basically, yeah, and sort of for very large classes.
Yeah, I mean, it would make sense as a solver, I think, because you don't need to prove that you have a normal form. I mean, you can just have a solver that tries.
Yeah.
I mean, that could be quite useful.
There's one small thing also, just to add. So I've used, I've written a small extension to the equational reasoning, where you can use tactic arguments with a solver inserted into it. So you can, for example, easily, so you describe this issue where you have this one equation you want to use, and the rest should be handled by the solver. Well, with this, you could basically say, I want to use the solver at every step, and then you only give the interesting equations in the parentheses of the solver. And this works quite well, actually, in practice.
Okay. Yeah.
So I can show you this later, maybe. It's very small, but it's kind of cute. It works nicely.
Right. Okay. Then let's thank Felix.